Welcome to the webinar, which focuses on aluminium surfaces at the School of Engineering here at Jönköping University. I guess people will come in even after we've started, but we will just have them joining us. You see from the participant list, which might be not the absolute latest one, since we have admitted participants just recently, but as you see, we have followed participants quite a lot from Sweden, of course, but also from all around the world. And that is pretty fun to see that we have so many joining us for this webinar within metal and polymer components manufacturing. Since you found your way here, I guess you know a bit about the event and the project, but the Veblen project is the project financed by the KK Foundation for us at the School of Engineering to provide quick and effective competence development within metal and polymer components manufacturing. We are planning between 30 and 40 webinars over 2 years, and this is our third webinar, but also the first in one module concerning I would say aluminium, but I'm not exactly sure if I'm right there, but I'm sure Katarina will correct me later. The ones you are meeting now is me, Stefan, who are a project manager within lifelong learning. And then further on during the webinar, you will meet Maximilian and Esan, both working here at the School of Engineering. Esan is the leader for the Veblen project. And the main characters that you will meet today are first, Professor Katarina Sanella, who will present an overview of durability strategies for aluminium. And then our guest speakers, Anders Skalski and Christian Verdinius from Provexa Surface Technology here in Sweden, where we will get their industrial experience and giving some real case examples of aluminium treatments. And then just a short agenda. We are pretty tight on time, so I will do a speed start. First, we have the webinar presentations coming up for around 45 minutes, maybe a bit more as it seems, but hopefully not more. And then we will have group discussions for half an hour, and then there will be a wrap up towards the end. And during the webinar, please have your microphones turned off if you haven't turned them off already. And if you have questions during the presentations, write them in the chat and we will answer those towards the end. And do please write them either to everyone, so everyone can see them, or write them to Maximilian. I'm sending it to anyone, but do write them to Maximilian or to everyone, since he will be the one picking up the questions. And please be active during our group discussions, of course. Since we will record the webinar, please turn off your camera if you don't want to become a star. But do turn them on again during the discussions, since those won't be recorded and it will be easier for the communication between us during those. And for those unfamiliar with Zoom, by this time in these days, you do have the mute function down below, and also where you turn off your microphone and also turn on and off your video. And then you have the chat function, which opens a chat box. Quite easy. And by that, I hand over to Katarina, and welcome again, everyone.
Thank you very much, Stefan, and welcome everyone virtually to Yon Shopping to listen to this webinar. Today, we will focus on aluminum surface, and this is a journey made of 3 different steps. The next one will be in May and then in June, and today we start with strategies for durability. So when we talk about surface technology, first of all, I would like to define what we mean. We can define 3 different classes of treatments. Either you add a material onto the surface, adding new material, of course, you make a deposition and you change the properties of the surface. Another way of doing that is by changing chemically and physically the material at the surface already from the bulk. And in this case, you would apply something that we call conversion treatments. Or you're interested just in changing the topography, modifying the texture of your surface. No matter what, all these 3 belong to what we call surface engineering, where you modify physically or chemically the surface of a material. But surface engineering should be considered as an integrated system of the surface treatment and substrate, because only when you design them as an integrated system, you will be able to give a new performance to the component that neither the surface treatment by itself or the substrate would be capable of by its own. So very often I've been asked, what is the best solution for? Which surface treatment would you choose for this application? Well, the answer, unfortunately, is that there is no absolute best solution. That's why to talk about strategies for durability. Each solution depends on the specific substrate material, the specific application, the geometry, and the environment you will be working in, so the working condition. Therefore, you should learn strategies to make the right decision, not just get answers. The main factors you should consider when focusing on this problem are, when we think about aluminum components especially, are mainly 3. And they depend on aluminum itself. Aluminum components very seldom is made by pure aluminum. We actually mainly work with aluminum alloys. And therefore, chemical composition of the alloy, it's really important, but also how those chemical elements are distributed in the material, it's really important. So presence of heat treatments and microstructural features are really important, because alloys usually show an heterogeneous microstructure. In aluminum specifically, you can have second phases or intermetallic particle precipitation. Moreover, when you work with the components, when you arrive to the surface treatment step, you usually have passed already many preparation steps, many manufacturing steps. And the quality of the surface that you achieve at the end of that chain of production step is also really important. So surface preparation at that point is really critical, and insufficient surface preparation is usually the main cause of the failure when we talk about durability. Aluminum is a great material, has a very high ratio between mechanical performance and weight, but very often is not enough to stand the environmental condition is exposed to. So why do we need a surface finishing? Specifically for aluminum, we need it for corrosion protection, wear resistance, so mechanical loads, surface hardening against scratches or impacts, and very often also to give a better appearance to the components, specific colors or finishing textures. And to do that, we have different options. In the world of surface finishing, we have so many alternatives to choose from: painting, conversion coating, anodizing, electrodeposition, polishing, and so many more. So before you can make the right choice for your product, I think it's important to understand what are the requirements. What do I need for wear resistance and surface hardening? Also here, the answer is not straightforward, because what type of resistance depends actually on what type of mechanical load you will face. But in general, we can find many common aspects. Definitely you need hardness at the surface, but this depends on the material you choose to apply to the surface of the component. What is really important and transversal to all the treatments, in order for that hardness to express the potential of in performances, you need adhesion. So that material you add into the surface has to adhere perfectly to the substrate. In this way, you will foster the improvement in the application. When it comes to corrosion protection, on the other side, also here, we cannot just give a straightforward answer. The corrosion attack depends on the environment. So usually, when you think about protection from corrosion, the first immediate answer is, let's put a barrier between the metal to protect and the environment. So let's make a conversion coating or a deposition of a new material to seal the aluminum to not face the environment. Again, in order to be able to exploit the potential of protection, you need 4 important parameters to be considered. Adhesion to the substrate, again, thickness and its distribution overall, the whole profile of the surface, quality in the coating, so no porosity should be there, the coating should be continuous in order to be a barrier, and low permeability to those aggressive elements that are in the atmosphere, humidity and pollution as the main factors. Which level of those 4 parameters do you need? Well, that depends on the atmospheric corrosivity. Different environment will attack the component at different grades. And to define how aggressive is an environment, there is an international standard that helps you. The ISO 12944 divides the atmosphere in 5 classes, depending on how aggressive this class is. And if you enter into the standard, you will find a description of what are the typical conditions for those aggressivity level, but also you find a way how to define and measure the aggressivity of an environment. So adhesion has been coming back both for mechanical durability as well as corrosion durability. So let's look a little bit in what adhesion is. Adhesion is given by those forces that connect the new material on the surface to the material in the substrate. It's a sum of different bondings that create between 2 different materials. And therefore, this force depends on the type of bonding and their strength, as well as the number of the bonding. Because we are adding and joining materials that could be very different, we can add metal on metal, but we can also add polymer on metal. There are many possibilities of which type of bonding we can create. From the most simple, that is mechanical anchoring, when we block and mechanically the new material into the one below, to chemical bonding. The strongest one will be the cross-linking, when we create covalent bonds, or diffusion, where material compenetrate each other. But we can create also what we call weaker bonds due to dipole interaction, electrostatic forces, and chemical attraction. So already in the choice of chemistry, we know which potential we can achieve for adhesion. Of course, if we are developing weaker type of bonding, like in this case, the adhesion we can expect is much lower compared if we create stronger bonds. So the first consideration we have to do is which type of material am I joining, so that we know which type of bonding it can be created. But the second important factor is how many bonding can I create? And in order to increase and improve adhesion, being such an important factor for durability, we have a little bit of strategies. Because the number of bonding depend on how big is the area of the interaction, we can prepare and modify the profile of the aluminum surface to make it a little bit rougher, so that the real surface area is increased compared to the nominal one. In this way, there will be more space for forming a higher number of bonding, and therefore increasing adhesion. So remember that by roughening the surface, what we really do is actually increasing the real surface, increasing the number of total bonding. Additionally, but difficult to perform, we can create a special profile by roughening to also add a component of mechanical anchoring. In order to have mechanical anchoring, though, it's not enough to have a rough surface. The surface should provide this type of geometry while real geometrical blocking can be done between the materials, and so simple to perform. Nevertheless, roughness, I repeat once again, is really important in order to increase the number of bonding we perform. We should also be really, really careful when we increase the roughness of the material, because if the profile that we produce between valley and top of the profiles, peaks, is too narrow, maybe the coating material is not able to penetrate inside the full profile, therefore providing voids and lack of adhesion between the two. So roughening a surface is important, but we should not exaggerate. There is an optimum value after which too much roughness can be counterproductive. And where is this threshold value depends on the viscosity of the material and the capability of the material to reach the narrowest profiles. So if we're talking about a paint, it depends on the viscosity of the liquid paint. If you talk about an electrochemical process, then it depends on the throwing power of the process itself, for example, and the capability of leveling. We prepare this surface and we say adhesion is so important, but we have, because it forms chemical bonding. But in order to understand which bonding we create, we have to understand what a real surface looks like. Does it look like pure aluminum? No. The real surface of a component is very different compared to the bulk material. This is due to the fact that aluminum component goes through several steps of manufacturing before arriving at the final shape. Therefore, the last 100 of microns, the really tiny space on the surface, is very complex. We can recognize several layers. Going from the core of this component and toward the surface, we see the normal composition and microstructure, and moving toward the surface, we start to see a layer of hard worked material where the grains are smaller and full of defects, and going forward, those increased stress transforms the material into amorphous, a little layer of amorphous material, on which almost always we find an oxide layer, on which there is a combination of adsorbed gases, contaminants, oil residues, lubrication residues from previous steps. So you can understand that such a surface cannot be ready to form new bondings with the material we want to add as a coating. Therefore, the most essential step in our strategy for durability is to design a cleaning step. We need to prepare the surface to remove those layers in order to expose fresh aluminum to form bondings in coating. So any surface finishing can express its potential and give the performances you are looking for only when we clean the surface. Surfacing, this is the overall name, is made of many steps. And we have to combine different strategies in order to remove that complex surface state. We should apply a mechanical preparation to remove everything that is solid, like oxides or impurities, and that helps us also to roughening the surface to increase adhesion. And then we have to apply a degreasing step where we use organic solvents or water-based soaps to remove everything that is organic in nature and are usually oils and lubricant residuals from previous manufacturing steps. And we go to the final step that is the activation step, pickling. And the surface activation is a chemical solution that is designed depending on the substrate. In case of aluminum, is very commonly an alkaline pickling that could be followed by even an acidic bismuthing step. So even pickling can be broken down in several steps. And all of these will prepare the surface to be really active. This activity, this reaction and bonding forming with the coating is the one that gives you the adhesion that you need and avoids the formation of defects in the coating. So if you concentrate your effort into the surface preparation, then you can adhesion and no porosity in your surface treatment. How should I choose then the surface preparation? That depends on the material you are working with. And when it comes to aluminum, we said we work mainly with alloys. Typical alloying elements that we should be really careful with are copper, iron, and silicon. Those three elements are really common in aluminum alloys, and they can be in solution in the structure, or they can form second phases and intermetallics of different types. Therefore, they produce an heterogeneous microstructure. And an heterogeneous microstructure will end up to be an heterogeneity in surface activity and capability of forming bondings with the next layer. And this is actually something we do a lot of research here at Jönköping University. So regarding copper, copper is really dangerous when we talk about aluminum alloys, because it increases the corrosion rate of the aluminum matrix. And when we expose the aluminum alloy containing copper into the preparation steps, usually it gets even enriched at the surface, increasing the alert we should put in this element. Iron, on the other side, also increases the corrosion of the aluminum matrix, but can be removed by the proper preparation. If we don't remove it, then it can create porosity. And even when we remove it, we have to be really careful, because when we remove the entire particle containing iron, we may leave behind void. And if that is not well designed, it can create porosities. Silicon is an element that is very common, of course, in cast aluminum components. And you know, it has a very low reactivity because it's not a metal. And therefore, having such a low reactivity, it provides bad adhesion, increases the potentiality to create adhesion. And being so non-reactive, it remains there on the surface, not really interacting with anything, and is a sort of impurity that can remain embedded in your coatings or in your pre-treatment conversion coating. Because adhesion is so important and because surface preparation is so important, we don't stop at cleaning the surface. We usually add something that is called pre-treatments. We want to transform the surface of the material with the goal to make the surface more homogeneous, to decrease the to hinder the problem given by elements like iron, copper, and silicon. In some cases, to passivate the surface to increase the corrosion resistance of the material, but very often to increase adhesion of the additional layer, especially if we work with paints that are of such a different chemical nature. Here we have really an endless choice of possible pre-treatments. I listed here just the most common. The absolute most common and most performant one until some years ago was the one based on chromates. But then we have phosphate, fluorotoluenates, treatment based on cerium coatings, silane, and so on. I think that is not really important what is the chemistry of the pre-treatment. What really it is important is to understand how they work so that we can, no matter which pre-treatment we choose, we can check it works properly in our case. So if you see in this microstructure, by pre-treatment, we create a conversion layer, very thin, some tens of nanometers on the metallic substrate. And in this way, we first barrier, but also we create a control chemistry and microstructure at the surface in order to control the formation of bonding to the coatings. So most of them work by formation of a thin mixed oxide layer at the aluminum surface. Chromate, for example, we have a chromate solution in which we immerse the aluminum, and they react chemically together by corroding a little bit the aluminum and form a mixed oxide containing both chromium oxide and aluminum oxide. In the other cases, the chemistry is more complex. You will see many more chemical reaction involved. But what you have to see is that at the very end, what we obtain is actually more or less the same, a mixed oxide layer containing aluminum and containing the main chemical ingredients that the pretreatment is based on, so aluminum phosphates or aluminum titanate oxides. So why chromium-6, the famous chromium-6 chromate treatments that work so well, need so many alternatives? There are two reasons. So first of all, chromates are based on chromium-6 salts, and our community regulation, the European compliance to REACH and also ROS, demand a reduction and control of the use of chromium-6 on commercial products and also in processes. And this is due to the danger provided by hexavalent chromium. In order to understand which alternatives you should use that is chromium-6 free, we should first understand why chromium-6 worked so well. So if this is the conversion coating, that is chromium oxide and aluminum oxide mixed together, and this is the aluminum substrate, okay, we have a passivation and conversion layer. What happens when we have chromates layer is that by any mechanical damages on the surface, the substrate would be exposed, having a hole in the protection system. But due to the structure of its coating that are made of hydrogen, some initial ingredients containing chromium-6 are actually entrapped in the layer and can be released after a damage is formed, reacting again with the aluminum substrate, reforming the converter locally. This is actually called self-healing capability. This is why chromium-6 based treatment worked so well. Not many of the other have this self-healing capability. So they work same, they can give the same quality as conversion coating, but what they lack is the self-healing capability. And I promise you that researchers like me are working really hard to find alternative self-healing mechanisms to include in the chromium-6 free pre-treatments. A little bit different pre-treatment is given by silane. Silane is a hybrid material, organic inorganic material, based on silicon and silicon oxide bonding that can react at high temperature to create network of structure. This reaction, if done in contact with the metal, can also happen with the first oxide layer of the metal. And therefore, if you do a pre-treatment based on silane, you don't only oxidize the surface into a known chemistry, but you are actually creating a covalent bond that is among the strongest bond chemically you can produce between the substrate and the pre-treatment. Moreover, you have still a lot of free bonding sites for the next level. And therefore, you can design this silane adding a functionalities that has chemically capability to bond further with the next layer. For example, if we have a polymer here, because we work with a paint, this hybrid material can form a covalent bond both with the metal and also a new covalent bond with the paint. So let's say that C-lane are those technology that join different chemistry, forming the strongest bond we can have. And therefore, the pre-treatment based on silane are those that can really target your question about best adhesion. If adhesion is what you're looking for, then silane is probably the answer. In the other case, the other pre-treatment, of course, increase the adhesion, but also give some corrosion protection, passivating the aluminum surface. They can be applied by immersion. So all your components are immersed completely in a chemical solution, or by aerosol and spray. So you see, not only the chemistry is important, but also the technology of application is important, because it's not only locally, the bonding that you form locally that is important, but it's also the capability to form the high quality bonding everywhere on your surface. And the components usually have very complex geometry, big and smaller size. So the application technology should be designed in order to maximize the quality of application and the capability to reach every point of the surface, depending on the complexity of the geometry. The immersion has the advantage to be able to reach any exposed surface because it's based on a liquid, and liquid will just wet everything. But it has the drawback that some liquid can remain as a residual in some parts that like holes or difficult geometries to reach, internal pipes and so on. The aerosol and spray has the advantage that does not leave any residual and produce much less waste, but is not as good in reaching every single point, also even the most shielded one in the surface. It's more difficult to reach everywhere by spray compared to immersion. The surface in order to control the chemistry, and then we add the final layer. Here we have different choices, and we will look into that very quickly. We can choose paint, organic coating. They are very complex composite material. We call them organic coating, but actually they are composite material made of many different elements. We have the binders, that is the main component of a paint, and there are so many choices you can do: fillers, solvents, pigments, and additives. What we have to understand is how a paint works, so you can use it properly. Usually added as multiple layer on the conversion coating layer. And if you look into it, you can see that has several components that you can choose. But a paint is not a perfect barrier, because organic coatings are actually permeable and sensitive to the atmosphere. Humidity, chlorides, pollution, and even the UV rays from the sun can degrade the organic coatings. And we call the sum of all this weathering. So the choice of which organic coating you want to choose depends on which one of these aggressive actors is dominant in your application. But of course, there are so many choices of chemistry and so many choices of application technology. You can apply it by spray, by immersion, and then you have a fast, cheap process, but is not very flexible and has a risk of contamination. Or you can go on water-based or non-solvent treatments, as powder coating or electrophoretic coatings. In that case, you have much more expensive treatments, but you avoid the use of solvents, you reduce the waste, and you create very protective layer, because those applications usually need a high temperature curing, so some temperature to create stronger bonding inside the coating and to the conversion layer beneath. An alternative is anodizing. In case of anodizing, you actually grow an oxide layer on aluminum alloys. There are several types of anodizing that is based on different process parameter. The most common one is the traditional one, where you form an oxide layer that has a very special structure that is nanoporous. You form like nanotubes on the surface. In the bottom, you have a barrier layer that gives protection. And then you have these nano containers that can fill up with any pigments, creating beautiful final aspects. At the very end, you should close these pigments by a sealing treatment. And so you start with the anodizing by applying an external current to the aluminum component. You immerse them in a dye pigment containing bath to give the final color. And then you close this porosity by a water or vapor treatment that transforms the top layer of the oxide into the hydroxide, increasing the volume and closing the porosity, ending up with a very nice color oxide surface layer. Or you can add a metallic coating on it. You can do it by electroplating or by electroless, and you can choose any metal you need for your purpose. But you have to be really careful, again, that when you work with aluminum, the challenge is the surface reactivity. The position bath for electroplating and electroless are usually chemically aggressive, and aluminum is really reactive. And therefore, no matter what process you choose, your main attention should be again in the pre-treatment. When you work with aluminum, you should apply a pre-treatment, most commonly a zincate pre-treatment that passivate the surface and put some zinc on it so that you can protect the aluminum while immersing in this electrodeposition bath so that you are building a strong metallic layer on it. So the quality of the final metallic layer depends actually on the quality of this pre-treatment intermediate zincate layer. And the quality of the adhesion depends on the alloying element, because the zincate will be formed mainly on aluminum, not so much on the intermetallic particles. And you can improve its quality by making a two-step application. Just be very careful, because if you choose metallic coating for your final finishing, you should be really careful about their behavior in case of defects. Be really careful, because if you put a metallic coating that is more noble than aluminum, and in case of aluminum, most of the rest of the metals are more noble, since aluminum is not so noble. In case of defects, you would create a galvanic couple between the metal on the coating and the metal in the substrate, actually accelerating the corrosion rate of the substrate in proximity of the defect. And the corrosion can proceed both in depth, but also underneath the coating, and therefore be not visible to you that are controlling the quality. Different is if you would be able to choose a less noble metal to give protection, because in that case, the galvanic couple would accelerate the corrosion only of the coating, providing actually extra active protection to the substrate underneath. And that can be exploited mainly for steels, not so much for aluminum, unfortunately. So if I want to sum up this overview about what do I need for durability, remember, first of all, that corrosion attack depends on the environment. So you should do an analysis of what is the exposure in your application field. After that, you define the corrosivity class of the environment. You have to take extra care on the requirements in the surface treatment. And those requirements are not so much on the final coating choice, but is on the adhesion to the substrate, the thickness you want to apply and the capability of having that thickness everywhere, the capability of the process to avoid defects and porosity. Check the permeability and weatherability if you work with organic coatings, and of course, choose a material with the hardness you need. So when you plan testing to check the quality of the choice you did, remember two important things. One, check them and do the testing in the relevant environment. different environments contain different aggressive elements, and do test these requirements, adhesion, thickness, and defects, more than the performance of the coating itself. Therefore, you have to test real components. You cannot test the coating, because the system is an integrated system and the final properties are given by the combination of the substrate, cleaning, pretreatment, coating, and on which process you chose to apply the coating itself. So the steps you should apply in your strategies is analyze the work environment, identifying the aggressive elements, define the required property to assure durability, define the combined properties, because often it's not just durability you are designing. You need color, conductivity, optical properties on the surface. Choose the material that will help you to give this performance. Choose the process to apply the material, considering limitation in geometries, in profile of the surface. Define the budget, of course, because we have different cost and economic impact of your choice, but then verify and measure the performance of the application of the coating as a whole. And with that, I would like to close this first part of the seminar. Thank you very much.